All right, well, good morning and happy Monday. It is it's fourth week Monday, so we'll continue on in talking about neural networks. So I think we kind of wrapped up Friday's lecture with backpropagation, and backpropagation we can kind of think this as like, how do we go about calculating the gradient of our loss function with respect to the different matrices that we're able to adjust. So we have two matrices of weights that we are able to adjust, and we're going to use gradient descent to optimize them. But in order to do that, we need to find the gradient of these matrices. One of the guiding principles is that when you calculate the gradient of that matrix, the gradient will have the same dimensions as that matrix itself. So W1 is a 2 by 3 matrix, and therefore the gradient with respect to W1 will also be a 2 by 3 matrix. And that allows us to do things like take the matrix plus and add the gradient, okay? Because that's basically what gradient descent does, is you start at a location, you calculate the gradient, and you multiply the gradient by a constant, and a negative constant, and you walk in the direction opposite of the gradient. So here we're going to have a 2 by 3 matrix for the gradient with respect to W1, and then we'll have a 3 by 1 matrix for the gradient with respect to W2. That's going to be what we'll do. We went over the calculation of these things. We said, okay, this is how we calculate the gradient of the loss function with respect to W2. It required us to introduce kind of these operations like element-wise multiplication. So we'll take this, the matrix of Y, which is n rows and 1 column, and we will perform element-wise multiplication by f prime applied to z3. Z3 is also n by 1, and we don't want to do traditional matrix multiplication. Traditional matrix multiplication kind of takes a row and a column and multiplies them and adds up all of those elements, and you get back a single scalar there. But we don't want that. We want to preserve the fact that it's still n by 1. And so, we introduced just kind of some additional notation to indicate that we have element-wise multiplication. And again, what we're doing is not strictly linear algebra. We're kind of playing a little bit with these numbers because, it provides a convenient notation for us to kind of work through. Okay, as we can continue on with the backpropagation, and we can ask, how do we find the gradient with respect to, say, W1? Okay, the beginning parts of calculating the gradient of the loss function with respect to W1 is similar to the beginning parts of calculating the gradient of the loss function with respect to W2. You basically keep applying chain rule until you reach the end. And so, with power rule, what's the gradient of that? The 2 comes down, you apply chain rule with -1, and then now we have to find the gradient of how does y hat change whenever we make changes to W1. And then we continue and expand this out, and we kind of went over this on Friday. And so, we said, okay, we'll find it with respect to how z changes with respect to a, and z is the product of a and w, so we end up getting W2 transpose there. Yes?
Sorry, if you went back to the backpropagation side, could you explain where you got the -1?
The -1 is because of chain rule. So as far as these terms go, yn is a constant. So we are looking at, for now, we're saying, okay, the gradient here is the total loss function is you take the difference between the actual value and the predicted value, and you square that difference, and then you do it for the first observation, then you do it for the second observation, third observation, so on and so forth. You add them up across all n observations. All of the y observations, y1, y2, all the way through n, those are all constants with respect to with respect to our weight matrix. So whenever, because we want to fiddle around with what W1 could be, right? There's 6 values in there, and we want to adjust them. If we adjust any of those values, those adjustments have no effect on the actual value y, but they do affect y hat. And so we're going to calculate how does y hat change with respect to W1. But as you do this, basically there's a negative sign here, and so you have to use chain rule after you do the thing, right? So it's, I don't know, if you just replaced it with like y minus x, and you said take the derivative with respect to x, or y minus x quantity squared, derivative with respect to x, you would do 2 times y minus x times -1. Yeah. Okay, so continuing on, we kind of keep working through this. We say how does z change with respect to an2, and we get W2 transpose there, and we ask how does an2 change with respect to W1, and well, this is an2 is the result. We're going to break that apart to an2 with respect to zn2, and then zn2 with respect to W1. an2 is the result of applying our sigmoid function f onto zn2, and so therefore how does it change with respect to zn2 is just the derivative f prime of zn2, or zn2. And again, right now, whenever you see the subscript, it just means we are looking at the nth observation, and then we have this summation sign at the front. So we're going to say we're going to calculate it for this nth observation, and do it for all of the observations, and then add them up. So the gradient with respect to the first observation will also be a 2 by 3 matrix. The gradient with respect to the second observation will be a 2 by 3 matrix. And basically you have this 2 by 3 matrix for the first observation, another 2 by 3 matrix for the second observation, another 2 by 3 matrix for the third observation, and then you're just kind of adding them all up. And then lastly, we have how does Zn2 change with respect to W1? During the forward propagation part, we said Zn2 is calculated by taking x, the nth row in x, and multiplying it by W1. So we have a 1 by 2 multiplied by a 2 by 3, and that gives us a 1 by 3. And again, it does feel weird trying to calculate how does Zn2, which is a 1 by 3, how does a 1 by 3 vector change with respect to a 2 by 3 matrix? And kind of looking at each of these things, the partial derivative ends up being a 2 by 1 matrix. Okay, it ends up being the transpose of the nth row in x. So so we have this, and if we put this in here again, the dimensions don't line up, and again, not doing strictly linear algebra, we kind of just rearrange terms in order to get what we know we want to get. So we know that this thing has to be a 2 by 3 matrix. We also see that this is not going to multiply out to be a 2 by 3 matrix. And so keeping in mind that we need this to be, we can kind of move this to the front. And again, it does feel very cheater-esque to do something like that. You could break this down into 6 components. Okay, you have a 2 by 3, and you can say, okay, well, what if we want to just do the top left corner? Okay, what if we just want to do top row, middle element, and things like that? And you can say, okay, well, which element would I be using, right? So with say Zn2, there are 3 elements, And if you say, hey, I want just the top left corner, then you would use the first element in Zn2, right? So it's because it's a 1 by 3, you would just use the first one. And then you're saying, okay, if I just want the top left corner, which element in Xn transpose? And you just use the top one, okay? And so you could break this down into all kind of 6 components of this CJ, sorry, this is DW1 matrix, and you have this kind of, and you can say, well, what if I want to do it for just this top element? So that one, you could reduce everything to just kind of scalars, okay? And if you do that, you'll find that you end up getting the same results. If you try to kind of take the, you have all 6 components and you say, well, can I expand this out to a nice convenient notation or easier notation using, what do you call it, linear algebra matrix multiplication? And the answer is yes, all right? And so if you do it, and you do it individually with scalars, and scalars you can kind of rearrange them, no problem, you can do that. But here I'm just kind of, I guess, jumping to it. And so we rearrange this, and if we take this, Xn transpose is 2 by 1. This whole thing for the nth element is a 1 by 1 scalar. W2 transpose is 1 by 3. F prime of Zn2 is 1 by 3. We do element-wise multiplication between this and this, which is going to result in a 1 by 3. And so the final result is going to be a 2 by 3 matrix. And that's going to be the result for just one observation, the nth observation, when we calculate the gradient for that one observation. And so right now, the total gradient is you calculate basically the gradient for just one observation, but you do it n times. So every single observation results in the 2 by 3 matrix, and then you're going to add them all up. You're basically stacking all of these 2 by 3 matrices on top of each other and adding them all together. And we can get rid of the summation sign using kind of matrix multiplication. And so if I get rid of this summation sign and the subscripts, basically instead of looking at just the nth observation in X, if I take the entire matrix of X, I get a 2 by n matrix. If I take the entire column of Y values instead of just the nth value, that's going to expand out to be an n by 1. Same thing with the Z matrix, Z3 matrix. Instead of just the nth observation, I get a column n by 1. W2 has no transcripts, or no subscripts, so it will remain a 1 by 3. It's going to be the same W2 values used for all n observations. And then Z2, rather than looking at just one row with 3 elements, we're going to get a matrix with n rows and 3 columns. All right. Is this okay? And so, so when we do this, the result of everything ends up being a 2 by 3 matrix. Okay, and again, I've written the subscripts underneath each of these matrices to ensure that my dimensions align, and I can do these calculations here. All right, and so so in the end, we end up with X transpose times delta 2. Delta 2 is defined as y minus y hat, element y is multiplied by f prime z3, okay, which we call delta 3, and we're going to do delta 3 times w2 transpose times f prime of z2. Okay, so we will go ahead and code all of this up into R. So let me. So, so we'll start. I'll get our data input, X and Y. And so you can see over here we have X is this numeric matrix. Let's see if I can. Okay, so right now these are our 3 observations. X has the has 3 rows with 2 columns, and these are the outputs. Okay, so X is 3, 5, and then results in 75. The input 5, 1 resulted in 82, and the input 10, 2 resulted in 93. Okay, and what we're gonna do is we're gonna just do a little bit of kind of numeric, I guess, cleanup, and that will, so if you think about the logistic function, it has values kind of mostly between, say, -3 and +3, because you've got this e to the negative t business. And so if you have a really large positive number, it basically asymptotically approaches 1, and if you have a really large negative number, you have, you know, something that asymptotically approaches 0, and the derivative, well, as it's asymptotically approaching, you know, you have this kind of this business. The derivative out here is almost 0, okay, and then the derivative out here down there is also almost 0, and so really we only get useful values when, say, between -3 and +3. And so what we're going to do is we're going to just kind of get all of our values, say, between 0 and 1, and that will kind of put us in the useful section of the logistic curve. So so one thing I did here was we're going to take X and divide it by the column max, okay? So I'm going to say, what's the largest value in each column? First column, the largest value is 10. Second column, the largest value is 5. So, so I do that, and then I'm divided by the columns. And so after I do that operation, what used to be, so the original values of X were 3, 5, and 10. Now I get 0.3, 0.5, and 1. And then here I divided this column by 5. I get 1.0, 0.2, and 0.4. And in order to do that, you know, I basically transposed the matrix X, because if I just did X divided by column maxes, which, you know, has the vector 2, 5, X over column max gets applied kind of funny, right? Because when you do some operation like this, R does it element-wise going down the columns. So it does 3 divided by 10, then 5 divided by 5, 10 divided by 10, and 5 divided by 5, 1 divided by 10, and 2 divided by 5. And so you get this. So I transpose it, and then I transpose the result. So transpose of X, so transpose of X divided by column max gives me exactly what I want, but I want this transposed. So, oops, didn't like that. Okay, and then we'll do something similar, but for Y, I've got values 75, 82, 93, and what I'm going to do is I'm going to just divide everything by 100, because if these are test scores, then our maximum value will be 100. So anyway, that is my X. Here's my current X. Here's my current Y. Okay. I have these kind of long names, but this allows me to kind of just change these to different values later. So right now, my input layer has 2 nodes, my output layer has 1 node, and my hidden layer has 3 nodes. And so I'm going to just put those values in there. And so then when I create my W1 matrix, I'm going to have the number of input layer for the rows, number of hidden layer nodes in the column, and so W1 ends up being a 2 by 3 matrix. Okay. Right now, for now, I'm just throwing in the values 1 in there. Okay. And then for forward feed, we'll calculate. So basically, I'm just let me just do forward feed, and let me pull this. Wednesday's lecture. So if you think about what we do in forward feed, we did x times W1, so I'll go ahead and do that. So I have x times W1, that results in Z2. So we ask, what are the dimensions of Z2? That's going to be n by 3. Okay, and right now our n is 3. And then what we want to do is we want to apply our activation function. Our activation function is 1 over 1 plus e to the negative z. And and I want to apply that element-wise to the matrix Z2. So I'm going to take our Z2 matrix, which is 3 by 3. I'm going to apply the activation function, and that will give me A2. So A2 is also 3 by 3, but now I've got all of these values in there. Our second weight matrix is 3 by 1, and so I'm going to do A2 by W2, that gives me Z3. A2 times W2 gives me Z3. Z3 is now going to be n by 1. Okay, so 3 rows, 1 column. You know what? I've completely forgotten. Let me give you your first view quiz answer, which is the letter A. Okay, and then we want to apply the activation function to that, which will still keep the same dimensions. And so if I do that, my y hat will be 3 by 1, 3 rows, 1 column. These are my current predictions. And so what we want to do is we want to define what is the difference between our our y values and our y hat values. So what we're going to do is we're going to take the difference between y and y hat, square them, add them up, multiply by 0.5. So I can say, okay, my current value is 0.75, my predicted value is 0.91. We'll take that difference, we'll square it. So this is our current loss. Okay, and it's real small because we only have 3 observations and everything's less than 1, but this is actually kind of a big number, okay? Considering, you know, our values are pretty poor estimates. Well, I mean, they're not, this one isn't terrible compared to that, but certainly we can do a lot better. So that's kind of the forward feed part. Now, remember the what we have is we want to get this. We want to get our gradients kind of coded up in there. Okay. So so we want to say, all right, this is what we're going to get for the gradient with respect to W1. This is going to be our gradient with respect to W2. So here is our f prime. Sigmoid prime is just our derivative of the gradient, okay, and it looks like this. And just so you can see that indeed this is the derivative of the gradient, here I'm going to just show you, here's our sigmoid function. Okay, so you can see as it approaches -6, it's just going to asymptotically become 0. Here asymptotically approaches 1, and then, you know, what is the derivative of the logistic function or sigmoid function? It's pretty close to 0 out here, pretty close to 0 out here, and then you have the greatest amount of slope right here around 0. So, so this is the plot of the gradient right here, or the derivative, sorry, derivative of f prime in green. You guys see that? Maybe I should do red. Okay. Okay, so so this part is just exactly what we said it's going to be. It's going to be, we did all of the hard work, and we said we're going to do y minus y hat, element y's multiply, times f prime of z3. So, oh, negative y times y minus y hat. So if we do that, we get exactly that. Okay, and so delta underscore 3 is 3 by 1, and then we're going to multiply that by the transpose of A2. So keep in mind our A2 matrix is 3 by 3. If we transpose that, and we do transpose of A2 times this, dj dw2 gives us a 3 by 1. So right now, our gradient is kind of all the same number. That's fine, but it'll get fixed. Over here we have x transpose times delta 3 w2 transpose element y's f prime z2, which reduces down to x transpose times delta 2, where you say delta 2 is all of this. So delta 2 indeed is going to be delta 3 times w2 transpose element y's sigmoid prime of z2. So here, whenever you see element y's multiplication, it's just the star operator and r. Okay, and then we're going to do x transpose times delta 2. And so here is the resulting gradient. And the resulting gradient there is 2 by 3, which is exactly what we want. Okay, dj dw1 we want to be 2 by 3 because w1 is 2 by 3. We want dj dw2 to be 3 by 1 because w2 is 3 by 1. And the way we'll do gradient descent is we'll just take an arbitrary scalar value. Right now it's 5. This is overly huge because I only have 3 observations. So like in your homework, in your next homework assignment, when you do some neural network stuff, you'll want a much smaller scalar value for your multiplier, just because you have a lot more observations. Okay, so and then we would take kind of right now our current estimates of W is all just ones and twos, or ones all over the place. So I would do something like this, and I would update what W1 is, and we get new values here, and I would update what W2 is, and we would get new values here as well. Okay, so and then we could calculate the cost here using our new W1 and W2 values. And so again, what does the cost function do? It's the difference between y minus y hats. So so our current y's are this, and our current y hats are this. So this is my kind of current cost function. The value of the cost function is 0.0153. And now that I've recalculated what W1 and W2 are, I'll go through forward feed again. So I'll do x times W1. That result, apply the sigmoid function to it. I get A2 times W2. And then I'll apply the sigmoid function there. These will give me new estimates of y hat. Okay, so slightly different. So my y hats used to be this, and now they are this. And we're asking, are these estimates better than these estimates? So these are the old estimates, these are the new estimates. and we want to see, did my cost improve? So if you do this, we get cost 1, which was 0.0153, and cost 2 has indeed gone down to 0.0125. Okay, and then so far that's a good sign. And what we want to do is we want to iteratively apply this, and hopefully every single time we do it, our cost function keeps going down and down and down and down. And after, say, 1,000 iterations or so, our cost function, we're hoping, is close to 0, and our estimates, we hope, are close to the original values. I'm gonna come back to this numeric gradient check, and I will explain that in just a moment. Okay, so this is what we can do just to kind of see this in play. Rather than just initialize my weight matrix with all 1s, I'm going to just pick some random values. Okay, so here I've got set seed, and I'm going to just RUnif6 and RUnif3 for what my W1 and W2 matrices are initialized to. So W1 being a 2 by 3, I just picked some arbitrary values. W2 being 3 by 1 matrix, I just have some arbitrary values. I think in another, because RUnif goes between 0 and 1, I think in a later homework example, I do RUnif minus 0.5, and that just slides the range of RUnif to be negative 0.5 to positive 0.5. So you get a mix of negative and positive values in there as well. But basically, I'm just picking some random numbers here to get for what our W1 and W2 values are. Okay, I'm also going to do create a vector to kind of keep track of our cost. And right now my scalar is an arbitrary value of 5, which again for now is really big, and in a larger data set you would definitely want a smaller scalar value. Okay, so what do we do in our loop? So this is basically it. This is training our neural network. And what I want you to see is that I want to kind of like remove this mysterious black box nature of the neural network. Because often when you hear a neural network, it sounds like the computer's doing magic, right? Like things are coming in and now it's able to tell you your picture's a dog, okay? And it feels like magic, but really, it's not. It's just these operations here. So I have another data set that's a little bit more interesting, and we'll take a look at it on Friday. Have you guys heard of the MNIST handwritten digits data set? Maybe, maybe not. Okay, so this was kind of one of the earlier applications of neural networks. I guess I'll talk about it Friday, but basically, and it counts as kind of image classification. So you think about, like, you take a picture and it says this is a dog, and you take a picture and this is a cat. Well, we started off with very simple examples where we had a picture and we asked the computer, we took a picture of a handwritten digit and we asked the computer, is this the number 3? Is this the number 2? Is this the number 9? Okay, so you have this tiny little image. It's actually 28 pixels by 28 pixels, so just this tiny little square image of some handwritten digit that was scanned and digitized. And then we just ask the computer, hey, is this a 0? Is this a 9? Is this a 2? Is this a 3? And we'll run it on Friday, and you'll see it'll work. It'll classify these things most of the time. Okay, and then and basically the technology that powers, you take a picture and you say, is this a cat or is this a dog, or what is that? It's basically just the same thing, but just with a bigger network, okay? And all of these things are just basically running off of this same thing at the heart of this, which is just kind of 3 little parts here, okay? One is we do the matrix multiplication to create our y-hats. So I currently have W are my current values of W1 and W2. Everything else, okay, is just the result of kind of the forward application. I have my fixed values of X, my input values, and then I just do forward feed things, right? I take the matrix X multiplied by W1. Oops, I keep hitting Shift Enter because I'm, that's what you do in Python. Okay, Control Enter. All right, so I do that times that, then I apply sigmoid function, and I do this, and I get my predicted values. These are my y hats that I get for the current values of W1 and W2. I have to recalculate this every iteration because with every iteration, W1 and W2 change, so the resulting y hats will also change. Okay. This step is technically unnecessary, but I like to do this so I can see how much has my loss function or my cost function improved. Okay, so I'm going to take my actual values of y, compare them to my current y hat values that I just calculated using the latest values of W1 and W2. Okay, so that would give me my cost. Oh, sorry, right now I have one. Okay. Then I want to calculate my gradients. Okay, so my gradients depend upon y and y hat. So I had to calculate the y hats. So I can do y minus y hat. And then these are just the calculations for the gradients. And so these are the matrix multiplications and operations that we do to calculate the gradients with respect to W2 and W1. And then so now that I have my gradients calculated, I will update what my W1 and W2 estimates are. I take my current value of W1, subtract off scalar times the gradient. That gives me my updated W1. I have my current W2 value, and I subtract off the scalar times the gradient. Okay? And that's what I do every single iteration. Now that I've done this, I have a slightly different W1 and W2 value, and I repeat the iteration again. And I say, okay, now that W1 and W2 have changed, let's recalculate what my y hats are. Now that I've recalculated y hats, I can recalculate what my gradients are. Now that I've got new gradients, I can update W1 and W2. And I repeat the process. And every single time, we're hoping my estimates of y hats get a little bit better in that they are approaching the true values. So you have the true values over here, the initial values, and we're hoping with each kind of step, we get something a little bit closer to the true values. And that's that, okay? So does that loop kind of make sense as far as how we go about training? So, so let me go ahead and just run all of this code. And let me give you your second weight matrix, the letter C. Oh, I'm sorry, second view quiz answer, letter C. I keep all of these things jumbled up in my brain here. Okay, second view quiz answer is the letter C. Okay, and so the results after doing this is we end up getting some values for W1 and W2. Again, this is the drawback. The drawback of neural networks is you get these coefficients, W1 and W2, and they have no interpretability, okay? Like, what is the meaning of this? Why is this one positive and why is this one negative? I have no idea, okay? It's not like linear regression where we say, hey, the coefficient for, beta 1 is positive 3, which means, when x1 goes up by 1, our y hat changes by positive 3 and things like that. We have no idea, okay? But what we can do is we can say, okay, well, what kind of predicted values did I get? These are my predicted values, 0.7499998, 0.820005, 0.92989. How does that compare to the actual values of y, which are 0.75, 0.82, and 0.93? And we say, oh, they're pretty good, okay? They're pretty close to the actual value. We can calculate the cost. The cost at this point is 10 to the negative 9, so we feel pretty good about that. And we can see, okay, well, how did the cost improve? And we can see, yeah, in the beginning, we started off at what, 0.015-ish or something. It dropped dramatically, and then it leveled off, and then somewhere it found some improvement. And then after that, once you get to 10 to the negative 9, how much more can you improve? You can look at the log function, and you see, okay, it went like this, and here it's just shrinking by some kind of positive constant, multiplicative constant, and that's what you get there. Okay. There's the optim function in R as well, which just does generic optimization, and we can treat this as an optimization problem as well. And for the optimization problem, we don't actually have to calculate any gradients, and it can do that. And so basically, you just give it a way to calculate the loss function, which requires you to calculate your predicted values y hat. But once you do that, you can also feed it into the optim function, and it gets you some pretty good estimates. Different starting locations can give you kind of different values as well. So your loss function, when you run this here, you get it converges to 10 to the negative 15 for the loss function, and you can kind of see the results there. Okay, let me go back to this numeric gradient checking. I got just a few minutes remaining here. So the idea behind numeric gradient checking, and I ask you guys to do this in your homework as well, I guess homework 3. The idea is we want to calculate, again, there's 6 elements in here, and we want to calculate these different kind of elements. So this is the gradient with respect to W1. So how can we do this? Okay, well, we think, well, what is our W1 matrix? This is also a 2 by 3. Okay, and I've got 6 elements in here. And what I want to do is, let's say when I initialize my thing, I'm guessing I'm going to just put in the number 1 here, okay? And we can say, all right, what does, when I do forward feed, right? I take my x and I multiply it by W1, and then I apply our function to that, and I multiply that result by W2, and then I apply our function there, okay, and this gives me my y hats. I want to know, okay, if this changes a little bit, because if you think about what is a gradient, okay, what you can do is you can say, all right, if I plug this in, I get my y hats. What if I, instead of 1, I put in 1.0001, okay? Everything else remains a 1, okay? And now I'm gonna plug this in, and I guess I'll call this WE for, like we've added a little epsilon here, okay? And I want to know, like, okay, how does my y hats change once I add this little epsilon in here? So basically, we'll do the same kind of thing. And maybe my estimates go from, say, so right now I might have like 0.74, 0.83, okay? And then after I do this, maybe my value becomes 0.7401, and this becomes 0.8298 or something like that, right? So we can see, okay, when I added this, my predictions changed just by a tiny bit, okay? And then I can calculate my loss function. What is the loss, okay? So if let's say the true values, y were 0.76 and 0.81. Okay, let's say these were the true values. Okay, so here my loss is, I don't know, whatever this is. 0.02 squared plus 0.02 squared. Okay, I'm calculating what's the loss here. And then now my loss is, now that I've changed, my y hats have changed because I've added this tiny little 0.001 here. Maybe my loss, I don't know, it shrinks a tiny bit, right? It got a little bit better. It went from 0.74 to 0.7401. So this is what, 0.0199 squared. So something a little bit smaller. And this is 0.0198 squared. Okay. So my loss function also changes a tiny bit. Okay. So I say, how much did my loss function change when I did this? So basically, we're thinking we're going to do, loss minus kind of I'll throw in my E here, loss E divided by how much was the little e here of 0.0001. Okay. And that will give you the estimate just for this one cell. Okay. And then you repeat the process. You set this back to 1. You repeat the process, so this is 1 again. But now you change this to be 0.001 or whatever it is, 1.001. You add a tiny little e there. And you want to see how much does all of this change now that you've altered this one. And you go through and you do it for all 6. Okay? And that's basically what numeric gradient checking is we're trying to get like an estimate numerically of what the gradient is by just adding a tiny little epsilon. In this case, I've got a tiny little e, 10 to the negative 4, and I'm going to add it first to the first element, then I'll do it to the second element. I have to repeat this with however many elements I have. So I have 6 elements, so I do this once for each element, and I'm going to calculate the difference between y and y hat for each of these things. Okay, we'll wrap it up there, and I'll give you your last view quiz answer.